In 1977, NASA launched Voyager 1 into space. It's now 15 billion miles away, traveling at 38,000 miles per hour. At that speed, it would take 40,000 years to reach the nearest star. But here's what keeps astronomers awake at night. Voyager isn't slowing down. It's not stopping. And in the total silence of deep space, its instruments detected something that shouldn't be there. A hum. A low-frequency vibration coming from empty space itself. And we have no idea what's causing it. The scariest thing about space isn't black holes or asteroids or radiation. It's something far more fundamental. Something we're only beginning to understand. Let's talk about what space actually is, because everything you think you know is probably wrong. You've been told space is a vacuum, empty, nothing there, just vast distances between stars and galaxies with absolutely nothing in between. That's not true. Space has never been empty. Even in the darkest, most distant regions of the universe, far from any star or galaxy, space contains about 1 hydrogen atom per cubic meter. That sounds empty until you realize how much space exists. The observable universe is 93 billion light-years across. That's 880 trillion cubic meters. Even at 1 atom per cubic meter, that's an incomprehensible amount of matter floating in what we call empty space. But it's not just atoms. Space is filled with quantum fields, fluctuating energy states that exist even in a perfect vacuum. These fields randomly generate particle-antiparticle pairs that pop into existence, exist for an infinitesimally brief moment, then annihilate each other. This happens everywhere, all the time. Even in the emptiest regions of space, quantum mechanics is creating and destroying particles constantly. Space is boiling with energy at the quantum level. And here's where it gets disturbing. We don't know why. Quantum field theory predicts this should happen, and experiments confirm it does. But when physicists calculate how much energy this process should generate, they get a number that's wrong by a factor of 10 to the power of 120. That's not a typo. Our best theory of quantum mechanics predicts the vacuum energy of space should be 120 orders of magnitude larger than what we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. We literally don't understand what space is at its most fundamental level. Now let's talk about what space does, because it's even stranger than what it is. Einstein's general relativity revealed that space isn't a static stage where events happen. It's a dynamic fabric that bends, warps, and curves in response to mass and energy. Imagine a trampoline. Place a bowling ball in the center and the fabric dips, creating a curve. Roll a marble near the bowling ball and it spirals inward, pulled by the curvature. That's what massive objects do to space. The sun warps space around it, creating the curved paths we call orbits. Black holes warp space so severely that not even light can escape. But here's what's unsettling. Space isn't just bent by objects in it. Space can bend on its own. It can expand, contract, ripple, and twist in ways that have nothing to do with matter. In September 2015, LIGO detectors measured gravitational waves for the first time. These are literal ripples in space-time itself, traveling at the speed of light, stretching and compressing space as they pass through. The waves LIGO detected came from 2 black holes colliding 1.3 billion light-years away. When those waves reached Earth, they stretched and compressed space by less than the width of a proton. LIGO measured that. We can now detect space itself vibrating. But here's the scary part. Space is always vibrating. Colliding black holes, merging neutron stars, even the Big Bang itself, all created gravitational waves that are still traveling through the universe right now. At this very moment, space around you is being stretched and compressed by gravitational waves from events that happened billions of years ago. You can't feel it because the effect is infinitesimally small, but it's happening. Space is not stable, it's not fixed. It's a churning, dynamic medium that responds to every massive event in the universe. and we're only beginning to map these disturbances. Now we get to the truly terrifying part. Space is expanding, and the expansion is accelerating. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us. The further away they are, the faster they're receding. This led to the realization that the universe itself is expanding, space itself stretching between galaxies. For decades, astronomers assumed this expansion was slowing down. Gravity should pull everything together, right? The expansion should gradually decelerate until gravity eventually halts it or even reverses it. In 1998, two teams of astronomers measuring distant supernovae made a discovery that won them the Nobel Prize and shattered cosmology. The expansion isn't slowing down, it's speeding up. Galaxies are accelerating away from each other. Something is pushing space apart, overcoming gravity, driving the universe to expand faster and faster. We call this force dark energy, but that's just a name for our ignorance. We have no idea what it is. We don't know where it comes from. We can't detect it directly. We only see its effects. And it's not a small effect. Dark energy makes up 68% of the universe. Dark matter accounts for 27%. Normal matter, everything we can see, touch and measure, atoms, stars, galaxies, planets, people, that's only 5%. We don't understand 95% of the universe. But here's what makes dark energy truly scary. It's getting stronger. As space expands, the volume of the universe increases. You'd think that would dilute dark energy, spread it thinner, but it doesn't work that way. Dark energy has constant density. As space expands, more dark energy appears to fill it. The more space exists, the more dark energy exists. The more dark energy exists, the faster space expands. The faster space expands, the more space gets created. It's a feedback loop with no end. Right now, galaxies outside our local group are moving away from us faster than light. Not because they're traveling through space that fast, but because space itself between us and them is expanding faster than light can cross it. This doesn't violate relativity because nothing is moving through space faster than light. Space itself is stretching, carrying galaxies along with it. And this process is accelerating. Eventually, the expansion will be so fast that light from distant galaxies will never reach us. Those galaxies will disappear from our view, not because they stopped existing, but because space between us is expanding too fast for their light to ever arrive. In trillions of years, if any civilizations still exist, they'll look at the sky and see only their own galaxy. Everything else will have expanded beyond the observable horizon. They'll have no evidence the rest of the universe exists. They'll think they're alone because space itself has isolated them. Let's go deeper into dark energy because what we're discovering is profoundly unsettling. The simplest explanation is that dark energy is the cosmological constant, a property of space itself. Empty space has energy, and that energy drives expansion. But this raises immediate problems. If space has energy, quantum mechanics says it should generate virtual particles constantly. When physicists calculate how much energy this should produce, they get a number so absurdly large that it would rip the universe apart instantly. Yet we're here. The universe is stable. So something is cancelling out 99.9999% of the vacuum energy. We don't know what. We don't know how. The math says the universe shouldn't exist in its current form. Some physicists propose dark energy isn't constant. It might be a field that varies over time and space, like the Higgs field. They call it quintessence. If dark energy is quintessence, it could be getting stronger or weaker. It could behave differently in different regions of the universe, and we'd have no way to predict what it does next. In 2019, the Dark Energy Survey found tentative evidence that dark energy's strength has changed over cosmic history. If confirmed, this means our understanding of the universe's future is completely wrong. We thought we knew how this story ends. Heat death. The universe expands forever. Stars burn out. Black holes evaporate. and everything fades to maximum entropy. A cold, dark, empty cosmos where nothing can happen anymore. But if dark energy is getting stronger, the ending might be far more violent. There's a scenario called the Big Rip. If dark energy accelerates fast enough, it will eventually overcome not just gravity between galaxies, but gravity within galaxies, then gravity within star systems, then molecular bonds, then atomic bonds. The universe would literally tear itself apart at the quantum level. Atoms would be ripped into their constituent particles. Space would expand so fast that nothing could hold together. Current estimates suggest this might happen in about 22 billion years. That's a long time, but it's a finite time. The universe has an expiration date. And here's the disturbing part. We don't know if those estimates are right. If dark energy is accelerating faster than we think, the Big Rip could happen much sooner. Maybe in a billion years, maybe in a million. We literally don't know because we don't understand the force driving it. Now let's talk about vacuum decay, the most terrifying concept in physics. Our universe exists in a particular energy state. Think of it like a ball sitting in a valley between mountains. The ball is stable as long as it stays in the valley. But what if the valley isn't the lowest point? What if there's a deeper valley on the other side of the mountain? Quantum field theory suggests our universe might be in a false vacuum, a stable state that isn't the lowest possible energy state. It's like water that's been cooled below freezing but hasn't crystallized yet. It's metastable, stable until something disturbs it. If our universe is in a false vacuum, quantum tunneling could spontaneously create a true vacuum bubble. This bubble would expand at the speed of light, converting everything it touches to the lower energy state. Inside this bubble, the laws of physics would be different. Fundamental constants would change. Atoms couldn't form. Chemistry wouldn't work. Life couldn't exist. And it would happen without warning. The bubble wall approaches at light speed, so you'd never see it coming. One instant you exist. The next instant, the atoms making up your body cease to be stable. The universe would be destroyed and replaced with something utterly incompatible with our existence. Physicists have calculated the probability of this happening. The current estimates suggest our vacuum is probably stable, but not certainly stable. There's a small but non-zero chance that quantum fluctuations could trigger vacuum decay. In fact, it might have already happened. Somewhere in the distant universe, a vacuum decay bubble could have formed billions of years ago. Right now, it's expanding at light speed, consuming galaxies, erasing everything in its path. We wouldn't know until it reached us, and then we'd know for exactly 0 seconds before ceasing to exist. The really unsettling part: high-energy particle collisions might trigger vacuum decay. Every time we smash particles together at CERN or other accelerators, we're creating conditions that haven't existed since the Big Bang. Some physicists worried the Large Hadron Collider could accidentally trigger vacuum decay and destroy the universe. Calculations suggested the risk is negligible, but not zero. We're experimenting with the fundamental fabric of reality, and we don't fully understand the consequences. Remember that hum Voyager detected? Let's talk about what it means. As Voyager 1 traveled beyond the solar system's boundary, its instruments detected a faint plasma wave oscillation, a vibration in the interstellar medium. Space isn't silent. It hums with the accumulated energy of countless cosmic events. But there's something else out there, something we're only beginning to detect. Fast radio bursts, sudden, intense pulses of radio energy that last milliseconds and release more energy than the sun produces in years. We've detected hundreds of them. We have no idea what causes most of them. They come from all directions. They appear random. Some repeat. Most don't. The energy levels involved are staggering, requiring exotic physics to explain. Some astronomers think they're neutron stars with incredibly strong magnetic fields. Others suggest colliding black holes. A few seriously propose they might be artificial, signals from advanced civilizations. We don't know. And that's what's scary. Space is broadcasting signals we can't interpret. energy is moving in ways we don't understand. And we're sitting here listening, trying to make sense of transmissions from across the cosmos. What else is out there that we can't detect yet? What's happening in the vast darkness between galaxies that our instruments aren't sensitive enough to measure? Every new telescope reveals phenomena we didn't expect. Every improvement in sensitivity detects signals we can't explain. The more we look at space, the stranger it becomes. We thought we understood the universe. We thought we knew the rules. But every discovery reveals how little we actually know. Space isn't empty. It's not passive. It's not stable. It's a churning, expanding, vibrating medium filled with energy we can't see, forces we don't understand, and structures we're only beginning to detect. So what's the scariest thing about space? It's not black holes. We understand those. It's not asteroids. We can track those. It's not even the heat death of the universe billions of years from now. The scariest thing about space is how little we understand it. We don't know what it's made of. We don't know why it expands. We don't know if it's stable. We don't know what signals are passing through it right now. We exist in a universe where 95% of everything is invisible to us, where the fabric of reality might collapse at any moment, where space itself is accelerating toward a fate we can't predict. And we're just beginning to ask the right questions. The universe is far stranger, far more dangerous, far more incomprehensible than we ever imagined. And every answer we find reveals 10 new questions we didn't know to ask. That's the scariest part. Not what we know, but what we don't. The vast ocean of ignorance surrounding our tiny island of understanding. Space isn't just the final frontier. It's the ultimate mystery. And we're only beginning to realize how deep that mystery goes. What do you think is the scariest aspect of space? The expansion, the vacuum decay, the signals we can't explain? Drop your thoughts below. And if you want more uncomfortable truths about the universe we inhabit, subscribe. Because reality is stranger than we imagine, and we're just scratching the surface.